This distance that scientists assume that the age of the universe is the same number of years. Although, as you already know, this may be only the limit of our vision. Nevertheless, the CMB cannot be seen by human eyes. The intensity of the first light is too low. This is due to the expansion of the universe, which we'll discuss later, which causes light waves to stretch and lose energy, so they are barely visible and are in the microwave part of the spectrum. Certainly, here's the entire text you provided, carefully rewritten as a single paragraph without omitting any words. Space, the final frontier, a realm of infinite possibilities and mysteries that have puzzled humanity for eons. From the vast voids that punctuate the cosmos to the very beginning of time itself, join us on a journey as we explore the enigmas of the universe and ponder its future. We'll travel back to the dawn of the universe, witness its evolution, and gaze into the distant future. We'll seek the boundaries of the cosmos and question if there truly is an edge to all we know. In the vast expanse of the universe lies a deep mystery that eludes our understanding, a mystery that stays our imagination and challenges our understanding. It is a question of what lies beyond the universe. As we travel through space, we're faced with the realization that our vision is limited and imprisoned within confines of our observable universe. What lies beyond these boundaries remains a mystery, a cosmic curtain that envelops the secrets of existence. The very concept of beyond becomes a philosophical problem. How can we comprehend the realm that lies beyond our perception? This is a challenge that pushes the boundaries of human thought, sparking our curiosity and encouraging us to seek answers. Everything we see, from the interior of a room to the most distant galaxies that can only be seen through huge telescopes, everything that can reflect or direct light to us, is the observable universe. Currently, the radius of the visible universe is 46.5 billion light-years. However, the age of the universe is only 13.8 billion years. How to explain this discrepancy? Well, it all comes down to the expansion of the universe. As a result of this expansion, the areas from which the light is emitted are moving away from us, and so we observe them at a great distance. These 46.5 billion light-years are the boundary of our universe, even if the entire universe is infinite. Modern cosmology does not know what may lie beyond the observed boundary. These cosmological limits or horizons are dictated by light itself. We don't see the night sky completely filled with stars because of the limits set by light. For example, light has a certain maximum distance from which it can reach observers on Earth, as if there were a spherical barrier around us beyond which there are billions of other distant stars and galaxies. This is called the particle horizon and the event horizon. However, these two concepts differ from each other. While the particle horizon establishes a distance from which light in the past reaches us now, the event horizon is a distance from the present to an observer in the future. But beyond these horizons lies another limit, the Hubble horizon. If space objects are beyond this boundary, it becomes impossible to see them even after billions of years. They are constantly moving away from us at the speed of light. So because of this, it seems to us that the universe is limited, although in fact it is just light itself that is limited. You're well aware that the light coming to us from bright cosmic objects doesn't travel at infinite speed. For example, the Sun is located 94 million miles from the Earth, in which case light will only take 8 minutes to travel from it. And the star Proxima Centauri is located 4.2 light-years away from the Earth, in which case light would also take about 4.2 Earth-years. So it turns out that we can only see events that happened a certain amount of time ago in the past. Yes, we can say that we look back in time when we look up to the sky at night. So to update our knowledge about some extremely distant objects such as the HD1 galaxy, which is located 13.4 billion light-years away, we would need to wait the same amount of time, provided there are no obstacles like black holes in the way of light. In particular, if we could examine this galaxy in detail, we would learn how our galaxy was formed in the early stages of the universe. Therefore, light detection is important for studying the evolution of the universe, and it is thanks to this that we were able to develop the Big Bang theory. The consequences of the Big Bang could not but leave a trace. Such a trace was found by researchers in the 20th century who studied theories of the origin of the universe. Back then, astronomers Penzias and Wilson picked up a strange signal with their radio telescopes coming from everywhere and with the same intensity. It turned out to be a remnant of the first light that appeared in the universe, cosmic microwave background radiation. In the early stages of the Big Bang, atoms could not form. Electrons and protons could not combine due to the extreme temperature. The radiation of photons, particles of light, was scattered from electrons or absorbed by them, and therefore light could not travel far. The universe was then as a dense fog. However, after 380,000 years, everything began to cool down. The first stable atoms appeared, so the cosmos became transparent and light was able to spread freely over long distances. And it is this light, with its temperature above absolute zero, minus 454 degrees Fahrenheit, that we record as microwave radiation, which can be seen in any direction from the Earth at a distance of 13.8 billion light-years. It is precisely because of nevertheless, despite its low power, the LHC allows us to look through the crack of the beginning of the universe as we know it. The whole image of the past is revealed to scientists. It is thanks to the LHC that we now know about the Big Bang scenario and how the world developed from singularity to this very moment. Thus, the map of the sky where you can see the temperature fluctuations of relic radiation is a spotted pattern where blue areas are below the average temperature and orange areas are above it. These spots allow scientists to study the evolution of stars and galaxies, since density changes, also called seeds of structure formation, have formed the hot and cold spots of the CMB. In addition, the larger spots, covering one angular degree in the sky, have become one of the proofs of the flat model of the universe. Smaller spots, in turn, have revealed a wealth of data on the composition and age of the cosmos. Thus, the study of the temperature features of the CMB has become another proof of the existence of dark matter and dark energy. Back in 2003, a group of astronomers led by D.N. Spergel found the amount of dark matter and dark energy exceeds ordinary matter by several times. According to the latest measurements, the amount of dark matter is 26.8%, dark energy is 68.3%. Finally, the CMB also revealed to scientists the approximate rate of expansion of the universe, 42 miles per hour per megaparsec. Thus, the CMB provides modern science with a wide range of information about the early and present universe, and in particular helps to understand what the future holds for it. It turns out that both the CMB and the space horizon limit what we can see from Earth. Let's now take a closer look at what space horizons are and whether we can still look beyond them. We've already mentioned that the cosmic particle horizon is an imaginary line that forms a boundary for the visible universe, setting a certain distance from which light launched in the past can travel to the observer. So if other cosmic objects are far from the horizon, we cannot see them now. However, our particle horizon is not static. Over long periods, the light still travels its gigantic path, and we begin to notice more and more objects, albeit with the help of special equipment. However, we will never see what is beyond this horizon. But what if I told you that there are ways around this limitation of our space interest? We can't see stars 100 billion light-years away directly, but some properties of our universe provide a workaround. Meet the neutrino, a tiny, elusive fundamental particle whose mass can be close to zero, but it's special not only because of this. The neutrino has almost no interaction with matter. That is, it can safely travel over an enormous distance at almost the speed of light. Since neutrinos are formed as a result of many cosmic phenomena such as nuclear processes in stars or supernova explosions, they can carry data about one of these processes to Earth despite a distance of hundreds of billions of light-years. In addition, they can be transformed into particles with even lower energy during their journey. It's precisely because of the elusiveness of neutrinos that scientists have tried hard to detect them. However, further development of ultra-sensitive detectors will allow better detection of neutrinos, and so in the future, thanks to these small particles, we may learn what it is like beyond the cosmic horizon. In addition to neutrinos, gravitational waves will help us explore the universe beyond our vision. These waves of time arise from the acceleration of massive objects such as black holes and neutron stars or the rotation of two stars around each other. As a result of such energy processes, such waves travel in all directions at the speed of light, destroying less massive objects and slightly increasing the distance between them. But when they reach the Earth, they no longer have their previous power and do not pose a threat. Although they are just as difficult to see, these wave remnants tell scientists not only what exactly happened outside the visible universe, but also at what distance. For example, in 2016, scientists from the Massachusetts Institute of Technology recorded the collision of two black holes 1.3 billion light-years from Earth using waves. Gravitational waves, like neutrinos, are a guide beyond our limited universe, and the development of technology to capture them is a key to our knowledge of the entire universe. But no matter how rapidly our efforts to learn the secrets of the cosmos develop, we're hampered by one serious factor. We can forget about the direct observation of stars and galaxies in the invisible cosmos for now because of the expansion of the universe. After the Big Bang, the expansion of the universe did not stop, although it slowed down considerably. Because of it, all objects in space are moving away from each other, and every 3.26 light years, this expansion becomes more rapid under the influence of dark matter, which is widespread in outer space. The particle horizon is expanding along with the universe. Therefore, the larger the horizon becomes, the more objects that will beyond it appear on our star maps. In particular, all the stars and galaxies that we observe now will never leave the boundary of visible space, although in the distant future, we will see the space objects currently close to us, and in particular the CMB, as very distant and less bright dots in the night sky. However, due to the same expansion, many objects abroad will be moving away so quickly that we'll never be able to detect the light they have emitted. The expansion affects another horizon, the space event horizon. It sets a limit for any emitted signals, beyond which none of them will ever reach the recipient. Currently, the radius of this limit is 16 billion light-years. So even if a galaxy is in one particle horizon but beyond the event horizon, we will never be able to interact with it. The emitted signal, for example from the Earth right now, will become longer and longer until it reaches frequencies that we're not yet able to pick up, and the object that emitted the signal will be moving away from the Earth. Therefore, we will not be able to make ourselves known to possible extraterrestrial life if it's too far away. Furthermore, in the distant future, even the galaxies with which we are able to communicate may become unreachable to us. The expansion is shaping the size of this horizon. Much earlier, it reached about 60 billion light-years, but now it is only 16 billion light-years. In the future, this distance will become smaller. In this case, we'll remain in our space bubble without the possibility of communication and scientific development. As an additional wall to this bubble will be another horizon, the Hubble horizon. This limit is a theoretical point at a distance of 14.5 billion light-years from us, beyond which the speed of space objects exceeds the speed of light. That is, the further the light-emitting object is from the horizon, the faster it moves away from us. For a photon, it looks like a race. The farther it is from the Earth, the farther it moves away from it. And only beyond the Hubble limit will the Earth stop accelerating. However, the Hubble horizon is also expanding, allowing distant light to reach our telescopes over time. Let me know if you'd like this broken into sections, revised for readability, or converted into a more formal article or presentation. 4.0. Here is your text rewritten as a single paragraph, preserving all original words and phrasing. In the future, we'll be able to see more and more traces of galaxies and stars beyond the limit, but the expansion brings with it not only positive aspects. In the very distant future, the Hubble horizon will collapse. It will begin to shrink and stop around the galaxies of the local group. After that, no light from other cosmic bodies, unlike the light that has already gone beyond, will ever reach our cosmological horizon. We'll be cut off from the entire universe. But that's not all. The event horizon, the Hubble horizon, will merge in about 10 billion years, forming a new horizon with a radius of 63 billion light-years, and then we will not see any events beyond this new boundary. After tens of billions of years, all light emitted beyond the limit will disappear forever. Despite human curiosity, the universe seems to set limits to preserve its infinite secrets. We're surrounded by spherical horizons that do not allow distant light to reach the Earth, taking away our ability to immerse ourselves in the study of the evolution of our universe. Moreover, in billions of years, these horizons will merge, blocking light from beyond the Earth and completely depriving humanity of hope of expanding its knowledge of the unlimited universe. However, the rapid development of modern technology will allow us to record more and more data about deep space in the future, thanks to neutrinos and gravitational waves, and even later we'll be able to establish new particle horizons on other planets. Although we cannot get rid of these limitations, we can manage them. It will take many more generations before we can leave our own horizon, but when we do, there will be an absolutely limitless number of other horizons that we will also cross one day. All that remains is to wait. Since the beginning of our species, we've looked up into the sky and pondered the vastness of the universe. We've counted the stars, charted the constellations, and dreamed of what lies beyond our tiny corner of heaven. But did we ever dare to think about the end? No, not the end of our fleeting human existence, but the end of time itself. What will the last days of the universe look like? What will we see, hear, and feel in those last moments? Will everything go out with a bang, or will something completely unforeseen happen? Throughout history, humanity has thrived on exploring the unknown, pushing the boundaries of our understanding. Today, we embark on the deepest journey, a journey to the very end of time. Like grains of sand in an hourglass, each moment brings us closer to the inevitable conclusion of the universe. But how and when will it happen, and what does it mean for us, mere mortal beings? Crossing unimaginable scales of space and time, we travel billions, even trillions, of years into the future, a journey not of distance, but of time, for the sake of exploring the ultimate fate of the cosmos. A journey to the end of time. Here we are, in the Anthropocene, in the age of man, our time, our era. This is an era defined by the colossal influence of our species on this blue-green sphere we call home. We have shaped, manipulated, and forever altered the very fabric of the Earth in the blink of an eye. Take the Holocene, an 11,700-year era in which all human civilization was born. It has nurtured us from our earliest days, from humble hunter-gatherers to modern, technologically advanced societies. The comfortable climatic conditions of the Holocene allowed us to flourish, to invent, to build. It gave birth to agriculture, to writing, to the very notion of civilization. Nevertheless, as we rushed forward, the losses on our planet became evident. Our relentless thirst for resources, our relentless expansion caused the changes that marked the end of the Holocene. Climate patterns are changing, extreme weather events are becoming the norm. Biodiversity is under threat. The equilibrium that has nourished us for thousands of years is teetering on the brink. Our actions have left an indelible mark on the conditions of the Earth and ushered in a new geological epoch, the Anthropocene. This is a chapter of Earth's history written by human hands. As we stand on the threshold of this new era, one question arises. What legacy will we leave to succeeding eras? Our journey brings us closer to the year 2500, revealing the dynamic changes the Earth would face. Earth's magnetic field, our protective shield against solar winds, is undergoing a belated shift. The North and South poles are reversing places, an event last observed 780,000 years ago. This amazing turn is disrupting our technology, forcing us to adapt in ways never before experienced. Let us be transported to the year 4385. We're witnessing the return of an old friend, Comet Hale-Bopp. It is a sight to behold, a bright trail of light illuminating the night sky, a vivid reminder of our place in the universe. Jumping to the year 5000, we're confronted with the grim reality of our past actions. The polar caps have melted, leading to a global sea level rise. Many coastal towns, once full of life, now lie underwater, relics of days long past. In the year 6000, a colossal asteroid looms on the horizon. Its collision with Earth is inevitable, causing a catastrophic event that will change life as we know it. The year 8000, we're witnessing an extraordinary celestial event. A distant star, having reached the end of its life, explodes in a spectacular supernova. Its glow outshines entire galaxies, a reminder of the ever-changing landscape of the universe. The Earth and its cosmos, perpetually in motion, reminds us of the impermanence of our journey. As we look at the star-studded canvas of the universe, we reflect on the trials and tribulations that lie ahead on our journey to the end of time. The hands of the clock move forward, 1 billion years. Our sun, the source of all life, begins to change dramatically. Its luminosity increases by 10%, scorching the Earth with unquenchable heat. As temperatures rise, photosynthesis ceases. By 1.1 billion years, the green carpet that once covered the Earth begins to fade, replaced by barren landscapes devoid of life. The air becomes thin, and the oxygen we need is depleted. The relentless heat is accelerating, and by 1.3 billion years, the Earth's once vast oceans are beginning to evaporate. What was once a blue pearl in the cosmos is gradually becoming a dried-up brown. The great seas and oceans turn into mere memories. Our journey brings us to the last chapter of Earth history. In the 7.5 billionth year, the sun, transformed into a red giant, consumes our once lush planet, marking the end of Earth's existence. Our home world, which has nourished us for billions of years, is now returning to the cosmic dust from which it was born. Fast forward to the year 10 billion. After its fiery death, our sun is reborn as a white dwarf, a weak, cooling remnant of its former self. From the raging hell of nuclear fusion, it's now just smoldering embers, a silent spectator to the grand cosmic drama that continues to unfold. By 100 trillion years, there's a deep silence over the cosmos. The stars, beacons of the universe, begin to go out one by one. They leave behind a chilling darkness, a universe in the twilight. By 1 quadrillion years, after the extinction of stars, the temperature in the universe drops. Having originated in the fiery origins of the Big Bang, we sink into cosmic winter, finding the universe gradually slipping into darkness. The era of starlight is over. The universe has become a cosmic graveyard. These are the last remnants of the stars that once illuminated the cosmos. They glow with a faint, ghostly light, a chilling reminder of the universe's fiery past. By 10 quadrillion years, these white dwarfs have become the dominant celestial bodies. This is the age of degeneration. It is a ghost universe that echoes memories of galaxies and stars that once shone brightly. The age of extinction is a vivid reminder of the endless cycle of birth and death in the universe. But even in its last gasp, the universe continues to evolve. Gravity, the sculptor of the universe, continues its work. Gravity, never resting, rips stars and planets from their orbits, hurling them into the cosmic void. These gravitational interactions sometimes lead to the birth of new stars, their creation heralded by ultra-bright supernovas, echoes of the past universe. Meanwhile, white dwarfs begin to disappear. Over trillions of years, they cool and shrink. Their light dims until they disappear altogether. Dying white dwarfs are reborn as black dwarfs. A black dwarf is a final evolutionary state of a star. Invisible to the eye, they mark the plunge of the universe into darkness. The era of black dwarfs begins. The universe, once a spectacle of light and color, is now a shadow of itself. The journey to the end of time continues in coldness and darkness. As time goes on, the universe continues its relentless expansion, each region of space stretching and thinning. Space-time itself is stretching. What was once an organized whole now expands endlessly into something like a multitude of distant islands lost in the boundless ocean. But within this void, a silent catastrophe occurs. Protons, the building blocks of matter and life, begin to decay. Protons, the heart of every atom, disintegrate into ghostly neutrinos and photons. Matter as we know it is disintegrating. The universe is slowly erasing the last vestiges of its physical history. All that remains are particles of light and black holes. At this point in the journey, the familiar physical phenomena end, plunging us into a new era of cosmic history. We are in the era of black holes. Even the seemingly eternal black dwarfs have disappeared, giving up their mass to the unrelenting pull of the expanding universe. The last remnants of stars have turned into cosmic dust. Black holes are becoming the main, if not the only, celestial objects dotting the universe. In an era dominated by black holes, the remnants of once living galaxies, supermassive black holes are of particular importance. Born from the deaths of massive stars and the merging of smaller black holes, these celestial titans have grown to incredible sizes, absorbing matter and energy on a scale beyond anything we could have imagined. These cosmic events emit gravitational waves, causing ripples in the fabric of space-time. We can think of them as the last sounds of the universe on the verge of its end, the slow ringing of a bell echoing through the vast cosmos. Such outstanding objects of the universe as black holes are not as eternal as one might think at first glance. The famous physicist Stephen Hawking in the late 1970s introduced a concept now known as Hawking radiation, the process by which black holes lose energy and therefore mass over time. This phenomenon is a result of specific properties of quantum physics near the event horizon, where pairs of particles and antiparticles appear. One of the particles is sucked into the black hole, which helps the other to break their bond and escape into space. This leads to a net loss of energy, and hence the mass of the black hole. Over enormous time scales, this slow leak causes a black hole to lose mass and shrink, and in this process, its once overwhelming gravitational pull slowly weakens. The result is the evaporation of a black hole. Such events mark the death of the last major objects in this universe, leaving behind a vast, seemingly endless cosmic void. Since the Big Bang, Our universe has been expanding under the influence of a special force we call dark energy, a hypothetical form of energy believed to permeate all of space and act as the antithesis of gravity, causing the expansion of the universe to accelerate. At the same time, dark matter, which makes up 85% of the matter in the universe, creates gravitational attraction, acting as a counterbalance to this acceleration. Although dark energy seems to be the dominant force at present, we must consider the possibility of a shift in the balance of forces. There are several theories suggesting that it is likely that more dark matter may emerge as the universe expands, slowly increasing its gravitational influence. If the gravitational influence of dark matter exceeds the force of dark energy, the expansion of the universe could begin to slow down and possibly even reverse. This is comparable to the elastic band effect. The universe stretches more and more before the moment of an abrupt contraction arrives. This process is also known as the Great Contraction. Great compression will inevitably cause the universe to collapse in on itself, the density of matter and energy to increase dramatically. At some point, we reach the critical point of this compression, the moment of peak density and temperature. Everything existing would be crushed into an infinitesimal point. In this extreme state, the fundamental laws of space and time are distorted beyond recognition. It is here, in this singularity, that another Big Bang could occur. Such a cataclysm could begin the birth of an entirely new universe, a new cycle of continuity of existence. This journey gives us a sense of our place in the cosmos. We realize that our existence is but a brief moment in the grand timeline of a universe. The journey to the end of time brings us to the very beginning, and perhaps this is where we find the greatest revelation. In a universe of infinite possibilities, the end is just another beginning. Music. More than once, you've caught yourself wondering what will happen in the future, in 100, 1,000, or even 1,000,000 years. And for you, we tried to look behind the screen of the future through the evolution of the stars we see in the sky every night to absolute oblivion. Today, we'll try to tame time and find out what our universe will look like in 100 million years. Check your seat belts. In a few seconds, you'll find yourself at the very beginning of the universe's life and travel all the way to its last moments. We're about to begin. Let me know if you'd like this formatted into a readable article, split by sections or time periods. Search, reason, deep research, create image. ChatGPT can make mistakes. Check important info. The universe may be hidden within ourselves. We all know that everything around us is made of atoms. Within the nucleus of an atom are two elementary particles, a proton and a neutron. These particles are generally considered stable within the nucleus, meaning they cannot decay. But what if this assumption isn't entirely true? The proton, one of the most common particles in the universe, can exist even outside the nucleus. It is considered stable due to the laws of conservation of energy, charge, and baryon number. However, according to the standard model of physics, the proton cannot decay, but emerging theories, such as a grand unified theory, which combines the three fundamental forces, electromagnetism, weak and strong interactions, suggest otherwise. In the distant future, proton decay is a possibility. While this process might not trigger a universal catastrophe immediately, if it occurs on a massive scale, then in millions or even billions of years, parts of the universe could cease to exist. Proton decay would destabilize atomic nuclei and release decay product that could gradually affect the structure of matter and the entire universe. Yet, the universe won't vanish all at once. Regions where proton decay happens would see disruptions in galactic evolution. Future humans might witness the decay of protons within their own bodies. This potential decay, perhaps within 100 million years, adds to the threats we already consider, like heat death or Big Crunch. If widespread proton collapse happens, it might trigger an even more terrifying end, the total annihilation of all matter through a phenomenon linked to the Higgs boson. The Higgs boson is a fundamental component of the Higgs field, a theoretical field that permeates the universe and gives particles mass through interaction. The Higgs field also affects what we call vacuum. Though we think of vacuum as empty space, it still contains quantum fields and has an energy state. A true vacuum is completely stable with the lowest possible energy, while a false vacuum is metastable, holding more energy and less stability. According to current theoretical models, our universe is in a metastable vacuum state. If a high-energy event, like massive proton decay, occurs, it could cause a transition to a true vacuum in a small region of space. This would create a bubble of true vacuum that expands at the speed of light, annihilating everything in its path: particles, matter, galaxies, and even the laws of physics as we know them. Life, in any form, could not survive such an event. The universe would evolve into something unrecognizable. While we can't predict exactly when or if this will happen, humanity will likely continue discovering more about the universe, and one day, these discoveries could tell the full story of both the cosmos and ourselves. Space is a final frontier, a mesmerizing cosmic tapestry of stars, galaxies, and nebulae woven together by the very fabric of the universe. But what happens when we find a breach in this grand design? Imagine the Boötes void, a region so vast and empty that even traveling at the speed of light would take over 330 million years to cross it. That's roughly 23 times larger than the Milky Way galaxy. The Boötes void is astonishingly barren, with a density of galaxies so low it challenges our understanding of cosmic structure. This isn't science fiction. This void is real and represents one of the universe's greatest mysteries. To understand its significance, we must look back. In the late 18th century, with the invention of the telescope, astronomers began mapping the stars. But it wasn't until the 20th century, with advanced technology and deeper sky surveys, that we realize our Milky Way is just one of billions of galaxies forming a vast cosmic web. This web consists of galaxy clusters, filaments, and enormous voids. What were once thought to be observational errors turned out to be cosmic voids, regions with far fewer galaxies. In the 1970s and 80s, redshift surveys revealed the universe's large-scale structure. Galaxies weren't scattered randomly, but formed patterns resembling a web with empty spaces, voids, between them. With digital technology and projects like the Sloan Digital Sky Survey, we created detailed 3D maps of the cosmos. This led to deeper understanding, though these vast voids continue to puzzle scientists. One such mystery is the Boötes void, discovered by astronomer Robert Kirshner in 1981. It spans about 330 million light-years in diameter, yet holds only about 60 galaxies, compared to the 10,000 we'd expect. Some galaxies inside it are oddly arranged in a tubular structure, a feature still unexplained. Another notable void is the Eridanus supervoid, stretching about 1 billion light-years across. Though not as empty as Boötes, it is linked to the cold spot in the cosmic microwave background, the afterglow of the Big Bang. Some scientists believe this cold spot is caused by the void via the Sachs-Wolf effect, where photons lose energy traveling through such a massive emptiness, resulting in a colder patch in relic radiation. Then there's the Canes-Venatici supervoid, located in the Hound Dogs constellation. This colossal structure spans approximately 1.2 billion light-years. Like a cosmic desert among a forest of galaxies, it raises a question: how could such massive voids form? Several theories have been proposed. One involves cosmic inflation, an explosive expansion after the Big Bang. Quantum fluctuations during this period may have amplified into dense and less dense regions. Matter gravitated toward dense areas, forming galaxies, and left behind vast voids. Another theory suggests that dark energy, the force accelerating the universe's expansion, pushed galaxies from less dense to denser regions, inflating voids. Additionally, as matter clumped into galactic structures under gravity, empty regions naturally formed in between, like bubbles in bread dough. Despite these ideas, many mysteries remain. The scale and complexity of the universe are daunting, and our knowledge of dark matter and dark energy is still limited. Yet, research continues. Digital surveys and simulations help scientists model how voids may have formed. The implications are profound. Studying voids helps refine cosmological models. If a model predicts void properties accurately, it supports a theory. If not, it might need revision or replacement. Void study has even inspired speculative theories, like the existence of alternate universes. Some suggest these empty regions could be interfaces to other dimensions, as postulated by certain interpretations of quantum mechanics and string theory. Though these ideas are not widely accepted scientifically, they challenge us to think beyond our universe. Other theories link cosmic voids to quantum fluctuations during the universe's infancy. These fluctuations may have seeded the density variations leading to today's voids, like ancient imprints on the universe's fabric. Further hypotheses delve into topology, the study of space and its properties. Irregularities in the fabric of space-time, possibly formed during inflation, could have prevented matter from accumulating in certain regions, creating voids. Black holes, particularly primordial ones formed shortly after the Big Bang, might also populate these voids. Their gravitational influence could clear surrounding matter, deepening the emptiness. Another compelling idea connects void formation to dark matter filaments, the scaffolding of the universe. If these filaments collapse or are disrupted, the flow of matter will be altered, potentially leading to vast empty regions. In this view, cosmic voids are not merely absences but structural result of underlying cosmic processes. These great voids, though once seen as empty, now stand as critical components of the universe's architecture, gateways to deeper understanding of matter, energy, and the very origins of everything. Here is your text transformed into a single coherent paragraph without omitting any words. Underscore 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 underscore. Dimensions others may be strikingly similar, may even again life as we know it. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? The multiverse concept challenges our understanding of our place in the cosmos. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating, it is also controversial. After all, if these other universes are beyond our reach, how can we detect or study them? And if the theory cannot be tested, can it be considered scientific? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding where science mixes with philosophy, and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. Our understanding of the universe rests on two pillars of modern physics: quantum mechanics, which describes a world on the atomic and subatomic scale, and general relativity, which describes a world of very large dimensions. But what happens when these two worlds collide? According to Einstein's general theory of relativity, space and time are interwoven into four-dimensional fabrics known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appear and disappear. It is a world that challenges our everyday logic. These two theories meet in the singularity of the Big Bang and in the heart of black holes, where the scales of quantum mechanics and gravity intersect. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. One exciting idea that emerged from this search is a no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity. Instead, space and time are finite but limitless, like the surface of the Earth. Just as you can travel the Earth without falling off the edge, you can travel the universe without colliding with a boundary. The universe would be a four-dimensional sphere, and the Big Bang would be a smooth point similar to Earth's North Pole but not a singularity. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we've discussed, the no-boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let's look into the field of string theory, a theoretical framework in which the fundamental building blocks of the universe are not particles but one-dimensional entities called strings. Each string can vibrate at different frequencies, and these different vibrations produce different particles. Electrons, quarks, photons, all of them can be strings just singing on different notes. But string theory doesn't stop there. It also predicts the existence of more than 3 spatial dimensions with which we are familiar. These additional dimensions may be compacted or hidden from our perception, but nevertheless fundamentally affect the fabric of reality. In the context of our topic, one variant of string theory, the pre-Big Bang scenario, or as it's also called, the ekpyrotic model, suggests that our universe may have been created by the catastrophic collision of two multiverse worlds or brands. What happens after such a collision? The two brands bounce off and apart only to come together gravitationally and collide again billions of years later, perhaps creating another universe. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brane parallel to ours. And yet, string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. And as we already know, such things are very difficult to verify. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum, we often imagine absolute nothingness. But in the world of quantum mechanics, the vacuum is far from empty. This is a bubbling soup of particles and antiparticles that spontaneously arise and then destroy each other. This phenomenon is called vacuum fluctuations. The vacuum fluctuation model, also known as a quantum fluctuation model, suggests that our universe may have originated from one of these vacuum fluctuations. A tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. Such a bubble, due to phase transition or quantum tunneling, would begin to expand rapidly, and its edges would be pushed outward by negative pressure. Inside this bubble, false vacuum energy could be transformed into matter, giving rise to stars, galaxies, and eventually you and I. So what was there before the Big Bang? In the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and antiparticles, and our universe was just one random bubble that managed to grow into something bigger. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions. For example, why did this particular bubble expand while others did not? And how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities. One of these possibilities is related to the field of research that combines quantum mechanics with cosmology. That brings us to the next model, the big bounce theory. Imagine a universe that expands, contracts, then bounces back elastically. That's the basic idea of the big bounce theory. Instead of a singularity in which all the laws of physics cease to exist, the big bounce theory argues that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into singularity. Instead, because of quantum effects, it returns to a very small size and begins to expand again, leading to what we now call the Big Bang. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models. However, unlike the oscillating universe theory, the Big Bounce focuses specifically on the transition point, the bounce between contraction and expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role in the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bounce from a contracting state to an expanding one. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. Can we find evidence for a previous phase of contraction in our present universe? Can we develop a quantum theory of gravity that can handle these extreme conditions? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being investigated. Understanding how this process can occur without violating the known laws of physics is a main obstacle to this theory. The Big Bounce theory does not yet fit within our traditional notions of time and causality. However, as always in science, there are competing theories. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand, something mysterious, all-consuming, but perhaps also creative, a black hole. Black holes, mysterious giants of a universe, formed by the collapse of massive stars, are regions of space where gravity is so strong that nothing, not even light, can leave it. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite and the curvature of space-time reaches an extreme degree. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So what was there before the Big Bang? It could be the inside of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effect of the parent universe? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics, quantum mechanics, which describes a very small, and general relativity, which describes a very large. Loop quantum gravity implies that space itself is not continuous but consists of tiny discrete loops. It consists of tiny indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the big bounce which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the big bounce scenario. Instead of collapsing into a singularity, as required by traditional Big Bang theory and the general theory of relativity, the universe shrinks to minimum size, but quantum gravitational effects become significant and counteract the contraction. Then the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in conventional sense, but a phase of the evolution of a universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity of the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. Nevertheless, if it is correct, it offers us an amazing picture, a universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion. Although these theories offer intriguing possibilities, for the most part, they are still in the realm of speculation. Each has its strengths, its weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. But the beauty of science lies in the process of exploration and discovery itself. Researchers around the world tirelessly study these theories and improve their models, and the study of even one theory goes a long way towards advancing the whole picture. So what happened before the Big Bang? In a nutshell, at this point, we don't know for sure. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking.